This is lesson 2 for the calculus course. This lesson is on the product rule for differentiation. It's going to teach you how to differentiate a product of two functions. In lesson 1, you learned about the power rule for differentiation. You're going to need that for this lesson, so make sure you've done lesson 1 already. Now, in this lesson, you might want to start off with the proof of the product rule. I did that in a separate video that I'll link at the top right now if you want to click over there and watch the proof. I'm not going to test you on the proof of the product rule, but it may be good to watch that proof just so you understand where it comes from. If you watched that video on the proof of the product rule, you'll see that if we have a function, I'll call that p at x, which is a product of two other functions, let's say function f at x and g at x, I'll call function f at x my first function and function g at x my second function. So it's a product of two functions. We can find the derivative of the product of those two functions. So we can find p prime of x by following the following rule. You do the derivative of the first function times the second function plus the derivative of the second function times the first function. So p prime of x equals f prime of x times g of x plus g prime of x times f at x. So if we follow that rule, you can find the derivative of the product of any two functions. So let's practice a few examples. And I'm assuming you know the power rule for differentiation for this. I'm assuming that you know the derivative of, let's say, the function x to the n, that power function. I'm assuming you know that that is n times x to the n minus 1. You bring the exponent down as the coefficient and reduce the exponent by 1. We're going to need that rule when doing these examples. And if you don't remember that, go back and watch lesson 1. So let's use the product rule to differentiate each of the following functions. And I specified use the product rule because I suppose if we're finding the derivative of the product of those two things, we could start just by expanding this out, getting it into standard form, and then find the derivative. And we would only need this rule for that. But I want you to practice the product rule for differentiation for this. So that means don't expand it out, differentiate it just like this. So the product rule for differentiation tells us if we want p prime of x, since we have a product of two things, first function, second function, I need to do the derivative of the first function. So I need to find the derivative of that, which is just 3. Multiply that by the entire second function, plus the derivative of the second function, and the derivative of that function is 2x, and multiply that by the first function. And then all we have to do is simplify this. So let's expand it out into standard form. So p prime of x equals, let's distribute the 3, and we get 3x squared plus 3. And let's distribute the 2x. So plus 6x squared minus 10x. And our p prime of x function is equal to, let's collect our like terms. Notice we have a 3x squared and a 6x squared. That's 9x squared. And I have a negative 10x, nothing to collect with that. And I have a constant plus 3. So there's my derivative of p at x. Now, I kind of skipped a step when I did this solution. This is typically what I would expect from you to show when doing a solution to a product rule question like this. But often there's another line before we actually take any derivatives that people show. I intentionally didn't show it first because I think maybe it overcomplicates it. But let me throw it in here just so you can see another way that we could show more work for this. So technically what we did, so this line is kind of an optional line. I'll do it in a different color. When we found the derivative of our p at x function, which is a product of two things, what we did was the derivative of the first function. Now, instead of actually just going right to its derivative, we could just write down that what we're going to do is find the derivative of it. And we can do that using Leibniz notation. We can do the derivative with respect to x of 3x minus 5. This means the derivative, so this right here, it means the derivative of 3x minus 5 with respect to x, which we did right here. It's 3. But this line is just showing that that's what we're going to be doing. So we need to do the derivative of 3x minus 5 times x squared plus 1 plus the derivative with respect to x of x squared plus 1 times 3x minus 5. If you look at other people's solutions or other material for this, you'll often see this line in there. Just understand that that line is just telling you find the derivative of that and find the derivative of that. which we just went straight to those derivatives here and here. So I'm fine if you don't show what I wrote in blue, but if you want to show that to communicate what's happening, go for it. Let's try another one. This one, the function's just called y. So you could write y prime, or you could write dy over dx. That's Leibniz notation. The derivative of function y with respect to x equals. We would do the derivative of the first function. So the derivative of 2x plus 3 is just 2. Multiply that by 1 minus x. Plus, we now need to do the derivative of this function, which is just negative 1, multiplied by that function. That's the product rule. We're just following the product rule. And I've got that rule kind of flashing at the bottom of the screen for you, just so you remember what we're using for each of these questions. Now I have to expand this in the standard form to simplify it. So the derivative of y with respect to x is equal to, let me do my multiplication. I'll distribute the 2, and I'll also distribute the negative 1, and then I'll collect all my like terms. So I've got 2 minus 2x minus 2x minus 3. And on my last line, let's collect our like terms. dy over dx equals negative 2x minus 2x is negative 4x, and 2 minus 3 is negative 1. Now, if you wanted that optional line above, I'll do that in blue again. So when we're finding the derivative of the function with respect to x, what we did was the derivative of 2x plus 3 and multiplied that by 1 minus x plus the derivative of 1 minus x and multiplied that by 2x plus 3. But I just went straight to the derivatives. The derivative of 2x plus 3 is 2, and the derivative of 1 minus x is negative 1. Now, for each of these examples, I used the product rule because we're in the product rule lesson, and the product rule for differentiation is going to be very valuable. But for these questions, like I said before, we didn't really have to do product rule. If you really wanted to, and the question didn't specify, we could have done either of these. And let me just erase part B and redo it without the product rule. I could have just expanded it, so I could have just rewritten the original function in standard form and then differentiated that. So I'm going to rewrite the original function. I'm not going to do any derivative stuff yet. I'm just going to expand it out. So 2x minus 2x squared plus 3 minus 3x. Collect my like terms. I have a negative 2x squared. 2x minus 3x is negative x, and I have my constant 3. And then now that I have this in standard form, I can just use my power rule for differentiation to get y prime. 2 times negative 2 is negative 4. Reduce the exponent by 1. And 1 times negative 1 is negative 1. Reduce the exponent by 1. And what I have is negative 4x minus 1. Exactly what we had when we used the product rule. It was probably even easier to do it this way. But the product rule is going to be valuable when expanding is not an easy thing to do. Let's do example 2. Let's do some applications where product rule is going to be helpful. Find h prime at negative 1, where h at x equals this product of two functions. Now, this product would be a lot more complicated to expand. I mean, we could do it, and then we could differentiate. But since we're in the product rule lesson, and I think it would be easier for this one to do the product rule, let's use product rule to differentiate this. We want the value of the derivative when x is negative 1. That's what we want. Let me just show you graphically what we're looking for. So in red is that function, the h at x function. What we're looking for, oh, and I have the tangent line being drawn at any x value I want. We want the slope of the tangent, that's what the derivative tells us, when x is negative 1. So let me just set x to negative 1. We want the slope of this tangent line, the tangent line that touches the function at an x value of negative 1. So we want to figure out the slope of that tangent line. Now, I have Desmos telling me it's negative 8, but how are we going to figure that out? We're going to have to find the equation of the derivative, plug negative 1 into it, and it'll tell us the slope of the tangent at that point. So let's start by finding h prime of x. So h prime of x, I would have to do the derivative of this first function in the product, if I'm following product rule. So 3 times 5 is 15. X, reduce the exponent by 1, it becomes 2. 2 times 7 is 14. x to the 1, and the derivative of any constant is 0. So that's the derivative of the first function. That needs to be multiplied by this second function here, plus, now I need to do the derivative of this second function. So 4x, that's the derivative of the first term, and the derivative of this term in the function is just 1. And the derivative of the constant is 0. That needs to be multiplied by the first function. Now, this is the equation of the derivative. It's not simplified at all. I'd have to expand it all out, collect all my like terms, which we could do. But this question doesn't ask for a simplified version of the equation of the derivative. It doesn't even ask for the equation of the derivative. It just wants us to evaluate the derivative at that x value. So what I would do for this question, I wouldn't bother simplifying. I would just go ahead and plug -1 into this unsimplified version of the derivative. So h prime at -1 equals, let me just plug in -1 for all of these x's. And when you're plugging anything in for x, make sure you always put it in brackets. Okay, I rewrote the equation of the derivative with x changed to -1 for all of them. And now that looks complicated, but the arithmetic is actually really easy. Make sure you follow BEDMAS, but -1 squared is 1, so 15 times 1 minus 14, that's just 1. So inside those square brackets, it simplifies to 1. Inside these square brackets, I would have 2 minus 1 is 1, plus 6, it goes to 7. Plus, now in these brackets, I've got -4 plus 1, that's -3. And in these brackets, well, -1 cubed is -1, so I've got -5 plus 7 is 2 plus 3 is 5. So if we evaluate this, I have 7 minus 15, that's -8. And that's exactly the value of the derivative when x is -1 that Desmos gave us as well. It tells us the slope of the tangent at an x value of -1 is -8. That's the instantaneous rate of change at that x value on the original function. Question 3. I can't decide if I like that I put this example in here or not, because realistically we would never use the product rule to find the derivative of this, or I wouldn't anyway. I would just expand it out and find the derivative. But it's going to be helpful to practice a product rule question like this, because let's say we had a product of functions like this down here, 2x times the square root of x plus 1. If you're finding the derivative of that product, well, you can't expand that out. When you have a rational exponent like a square root, you can't just expand a 2x into it. You would actually have to use the product rule for that. So the product rule is very beneficial. So I just put this one in here just to give you kind of a hard practice of a product rule. Find the derivative of this function, x times 1 times 2x times x squared plus 3. And looking at it, what I would probably do, since it's a product of 3 things, I mean, there's a bunch of things we could do. What I would probably do, I would probably expand this 2x into this so that my g at x function was just 2x squared minus 2x times x squared plus 3. And then I could do product rule from there. Then I could start finding the derivative. So in order to do that, since it's 3 things being multiplied, we're going to think of these 2 things being multiplied as like the first part of the product. Think of that as the first function in the product. And think of this as the second function in the product, and then we'll follow the product rule, which tells us to find the derivative of this, do the derivative of the first times the second, plus derivative of the second times the first. But when we do derivative of the first, it itself is a product that we would have to use product rule for. So off to the side, I've given us space to find the derivative of that first function, the stuff I've coded in red. So the derivative of the first function would be equal to, well, I do derivative of x minus 1, which is 1, times the second part, 2x, plus the derivative of 2x, which is 2, times the first part, x minus 1. And then that could be simplified. 2x plus 2x minus 2 And that would be equal to 4x minus 2. So let me I just want to erase this to make it look neater. I'm just going to put the 4x minus 2 up there. So we figured out the derivative of that first function is 4x minus 2. So when I follow product rule, when I do the derivative of g at x, so g prime of x equals, I do the derivative of the first function, and keep in mind I'm counting everything in red as the first function. So I do the derivative of the red, which is 4x minus 2, times the second function, so that's the blue part, x squared plus 3, plus the derivative of the second function, the blue part, so 2x, times the first function, which is everything in red, so x minus 1 times 2x. And now that's the derivative, it just needs to be simplified. So g prime of x equals, let me expand this out. So I'll do my multiplying. I'll multiply that, and 2x times 2x, that's 4x squared. So if you don't mind, on this first line here, instead of having a 2x times a 2x, and you could do this on a separate line, I just don't feel like writing it, 2x times 2x, well, that's 4x squared. So I'm just going to put a 4x squared here, and then distribute that 4x squared to the x and the negative 1. So let me do all of that multiplying. So 4x cubed plus 12x minus 2x squared minus 6. Now I'm doing this product plus 4x cubed minus 4x squared. And now collect my like terms. I have 8x cubed. I have a negative 6x squared. And I have a 12x and a negative 6. So there we go. We could have also just expanded this all out completely before doing any derivative, and then just used the power rule, and that would have been fine too. Example 4, determine an equation for the tangent of the curve y equals x squared minus 1 times x squared minus 2x plus 1 at x equals 2. So let me just show you in Desmos what we're actually looking for, and then we'll come back and do it algebraically. So here's the red curve, and what we're looking for, so this is the original function in red. What we're looking for is the equation of the tangent line which touches that function at an x value of 2. So I have that graphed in blue here. We want the equation of that blue line, the tangent line which just touches the original function at an x value of 2. So they share this point right here. We know tangent lines touch the function at one point, and we're interested in the tangent line at an x value of 2. So we know the tangent line and the original function share a point at an x value of 2. So we're going to need the y-coordinate of that point, so we would plug 2 into the equation of the original function, because we don't have the equation of the tangent line to plug it into. And they share that point, so we can plug it into the original, and it'll tell us the point that the tangent line shares with it. So it'll give us a point on the tangent line. So plug 2 into the original function, it'll give you the y value of 3. So we now have an xy value on the tangent line. We also need the slope of that tangent line. To find the slope of a tangent line, you need to use the equation of the derivative. That's what the derivative tells you. It tells you the slope of the tangent at any point we want. So we find the equation of the derivative and plug 2 into it. And Desmos is telling me, if we do that, we should get a slope of 10. So we would have the slope, we would have an xy point, we could write the equation in y equals mx plus b form if we used those three pieces of information to solve for b, the y-intercept, and we should get, according to this graph, we should get negative 17. And then we could write the equation of the line to be y equals 10x minus 17. Let's go ahead and try that. So let's start by finding a point on the tangent line. Point on tangent line. Now, like I was saying, the tangent line shares a point with the original function when x is 2. So to find the point on the tangent line when x is 2, we know it shares the point with the original function, so we can actually plug 2 into the original function, and it'll give us a point on the tangent line as well. So we're finding the value of, this function is just called y, so I'll say we're finding y at 2. So that would be 2 squared minus 1 times 2 squared minus 2 times 2 plus 1. And we can evaluate this. 4 minus 1 is 3, and then 4 minus 4 plus 1 is 1. We get 3. So that tells us the point 2, 3 is the point where the tangent line touches the original function. So this is an xy point on the tangent line. We're also going to need to know the slope of the tangent line. Slope of tangent. So I'm going to need to know the value of the derivative of the original function when x is 2. That will tell me the slope of the tangent at an x value of 2. So we're going to need to know the derivative. I need to know y prime. So y prime equals, oh, this is a product of two things, function times function. So I can use product rule. So I'll do the derivative of the first function, 2x, times the second function, x squared minus 2x plus 1, plus the derivative of the second function, which would be 2x minus 2, make sure it goes in brackets, times the first function, x squared minus 1. Now, we can simplify this before we sub in an x value of 2 if you want, but I don't want to. Why don't we just sub it right into here? Let's find y prime at 2. So we'd have 2 times 2, 2 squared minus 2 times 2 plus 1, plus 2 times 2 minus 2, times 2 squared minus 1. Okay, let's evaluate this. I'd get 4 times 1 plus 2 times 3. Y prime at 2 would equal 4 plus 6. That's 10. That tells us the slope of the tangent at an x value of 2 is 10. So our m value is 10. We can now write the equation of the tangent line. Because we have 3 pieces of information in our y equals mx plus b formula, we can solve for b. So our third step is to find the equation of the tangent line at an x value of 2. So the equation of any line is y equals mx plus b. We have x, y, and m, but we don't have b, so let's solve for it. Let's sub in what we know. Y is 3, m is 10, x is 2. If we solve for b, we would get negative 17. So the equation of our tangent line, our final answer, y equals 10x minus 17. There's the equation of the tangent line. In Desmos, let me just show you that that is the correct equation. Let me write the equation y equals 10x minus 17. And notice that that went right over top of the tangent line that Desmos graphed. Last example, example 5. Student Council is organizing its annual trip to an out-of-town concert. For the past 3 years, the cost of the trip has been $140 per person. At this price, all 200 seats on the train were filled. This year, Student Council plans to increase the price of the trip. Based on a student survey, Council estimates that for every $10 increase in price, 5 fewer students will attend the concert. So this is a classic type of optimization problem. Let's see what this question asks us to do with this. Write an equation to represent revenue in dollars as a function of the number of $10 increases. So it tells us n in our equation is going to stand for the number of $10 increases. Well, revenue, that's how much money you bring in. Revenue is always going to be equal to, revenue based on number of increases is equal to, it's how many you sell, so number sold, times, well, how much did each ticket cost? So number of tickets sold times price per ticket. Okay, let's come up with an expression for each of those. So the revenue function equals number sold. Well, it says they sold 200 seats, but for each one of those $10 increases, 5 fewer people are going to attend the concert. So they would sell 200, but they're going to expect to have 5 fewer people every time they increase the price by $10. That's what this expression says. Number sold equals 200 minus 5 every time they increase the price by $10. Remember, that's what this tells us N stands for. Now, price per ticket. Last year they were $140, but they're thinking about increasing the price by $10 a certain number of times. So the new price is going to be 140 plus 10, how many ever times they decide to increase the price. So this is our revenue function. This would tell us how much money they bring in. Part B says, determine expression in simplified form for the derivative of the revenue with respect to the number of price increases and interpret it for this situation. So this is just Leibniz notation, meaning the same thing as find r prime of n. Same thing. And interpret it for this situation. Okay, r prime of n would equal, well, we have this in factored form. It's a product of two things. So let's practice the product rule. So I do the derivative of the first function times the second function plus the derivative of the second function times the first function. Hopefully you're getting the hang of the pattern here. So the derivative of the first function is -5 times the second function plus the derivative of the second function times the first function. So this is the equation of the derivative. This is the rate of change of the revenue with respect to the number of price increases. It tells us how the revenue is changing at any specific number of price increases. Let's simplify this a bit. R prime of n equals, let me just expand it out, -700 minus 50n plus 2000 minus 50n. And let me collect my like terms. I've got -100n and plus 1300. So there's my simplified equation of the derivative. And like I said before, I'm not going to write it down, but what does this expression mean for this situation? It tells us how the revenue is changing at any specific number of price increases. So it says, when is r prime of n equal to 0? This maybe is jumping a little bit ahead to next unit with why this is important. But figuring out when a derivative is equal to 0 is a crucial part of calculus. It helps us find max and min values. It helps us find what we call critical points on a function. And that's great for when we do optimization questions. So determine when r prime of n equals 0. When's the derivative equal to 0? So let me set the derivative equal to 0. And let's solve it. So I've got 100n equals 1300 and n equals 13. So that is when the rate of change of the revenue is going to be 0. Now, graphically speaking, it may help if I graph the original function and its derivative, and we can kind of make a connection as to what's going on here so we can answer this part. What information does this give the manager? So let me put these functions in Desmos. Okay, in red is the revenue function. That's our original revenue function, the product of the number sold times the price. Now notice, oh, and I also have the tangent line graphed. Remember, the derivative tells you the slope of the tangent line. So the revenue was 28,000 if they left the price the same. If they didn't do any price increases, the revenue is 28,000. That's what they made last year. But notice, if they increase the price, along the x-axis is number of price increases by $10. So if they increase the price once, the revenue is going up, up, up. The revenue keeps going up until we get to 13 price increases. That's when the revenue is at the highest. The revenue is at $36,450. After that, if they increase the price again by $10, the revenue, the red function, starts coming back down. Notice the tangent slopes were all positive before 13 price increases. These tangent slopes right here, if you pay attention to them, they're positive. That tells us the rate of change of the revenue is going up. It's increasing. And then after 13 price increases, look at the rate of change of the revenue. The tangent slopes are all negative. But what happens right at 13? The tangent line is horizontal. And what's the slope of a tangent line? It's 0. So if you have a horizontal tangent, that's what we call a critical point, and it could indicate a max, a min, or it could be neither. We'll talk about more about that in Unit 2. But for now, just notice that this revenue function, which is a parabola that opens down, So we know that if we can figure out where the tangent is 0, that means we're at the max point. We're at the point where the revenue is at the highest it can get. So setting the derivative to 0 and solving figures out the x value that would bring us to a max revenue. So we figured out 13 price increases is going to be the number of price increases that gives us the maximum revenue. So let's write that down. Therefore, 13 price increases will give a max revenue. And if we want to know what that maximum revenue was, we would just plug 13 into the original function. Plug it into this original function, and according to Desmos, we would get 36,450. If we were interested in, okay, at that number of price increases, how many people are going to come? Just plug 13 into this equation, and we would get 65. We'd get 135 people would come. So let me just quickly evaluate this actually. So R at 13 would equal, we'd have 200 minus 5 times 13, that's 135. So we'd sell 135 tickets. And if I plugged 13 into N here, I'd have 130 plus 140, that's 270. Each ticket costs $270. That's an expensive ticket. So they're able to raise the price of the ticket quite a bit and able to maximize their revenue. I mean, they're not going to fill the train, but based on the amount each person is paying for a seat, that's how they're going to maximize the revenue. And the product of those two things is what gives us our max revenue of $36,450. So I hope you were able, let me write that down. Give a max revenue of R at 13, which was $36,450. Okay, so that's it for our product rule lesson. Hopefully you feel comfortable with the product rule of differentiation. And in the rest of the unit, we're going to be looking at quotient rule and chain rule as well. So we'll learn lots of derivative rules in this unit.